Hi everyone and welcome back to my channel A in Economist. So in the previous session we have covered concavity and convexity in details. Now it's time for us to study the single variable optimization. Now if you haven't watched my concavity convexity video, I would request you to go through that video first because that will help you in understanding what is single variable optimization and how it is related to this chapter, right? Thanks for joining in, and now let's get into the topic. Now optimization is a very important topic from the economics point of view because economics can be defined as a science of choice. As economists, we always try to maximize our satisfaction, maximize our profit, maximize our revenue, right? So we try to maximize using the limited resources that we have. So maximization and minimization is the fundamental of every economic problem that we deal with. Like the day you will be associated with economics, you will be either maximizing things or you will be minimizing things. So you have to be very clear how to do this. It's very important and essential chapter for your further economic knowledge, right? So economics is the science of choice. So we either try to find out maximum value or the minimum value of the function in terms of choice variables. Now what do I mean by the choice variable? Suppose you have a function like this. Y is function of x. Since we are dealing with a single variable, that is what you have in your first semester exam. So I will be talking in terms of only this function. So y is function of x. Here what you have, only one explanatory variable or x variable, right? This is also known as the choice variable. This variable is also known as the choice variable. Why it is so? You can freely vary this variable. It is called the choice variable because you can choose the value of this variable according to your circumstances or according to your need, right? And the way you will vary this value, it will affect the value that this function will take, or the functional value, that is y, in terms of y, which is also called the dependent variable. Y is the dependent variable, or you also call it explained variable, right? You call it explained variable, and this x variable is called the choice variable. It is also called the explanatory variable, or it is also called the decision variable, and so on and so forth, right? So what you have to do in this chapter is that you have to find out that optimal x value. All we need to do, we need to find out the optimal x value that will give you the maximized or the minimized value of this particular function fx. That will give you the maximized value or the minimized value of this function fx. Now we will later on see optimization does not always give you the optimum value. Optimization process, the value that you find in this optimization process does not always give you the optimal value. It is not necessary. That we will come in this session. That might not be always the optimum value. So this optimization process is also known as the process of finding the extremum. The process of finding the extremum, right? Extremum means the extreme values. That is the, again, the same term for the maximum value and the minimum value. So often optimization process is known as the extremum process, or finding the extremum value. Why this is so? Because the optimized value may not be always optimum, right? And in economics, since we are always dealing with the choice problem, so it is very crucial that you understand these basics, right? Now let me graphically explain what this all about, right? So again, you have the function y equals to fx, and the domain of the function is a to b. See this graph, here you have a and here you have b. This is the domain and this is your graph, this black line. This is your function. This is fx. This is the function you have. Now if I ask you in this domain, this is the domain, right? This line is the domain. Now if I ask you in this domain, for which value of x the function takes the maximum value, if you analyze this entire graph, you will see corresponding to the value A, right? Corresponding to the value A, if you see, this is the maximum value. Then after this point, the function goes like this, this, and this, right? So corresponding to the value A, the function takes its maximum value, which is f of A, right? Now similarly, if you see this entire domain and entire function, in which value or at which value the function takes the lowest value or the minimum value, if you see carefully, you will see that at the point beta, when x equals to b, sorry, not beta, it's b, when x equals to b, the function takes the lowest value, which is f. So what you can say, in this entire domain, if you consider the entire domain, then what you see is that at x equals to a, the function has a global maxima. Graphically, I have not gone into the mathematical part yet, only graphically by looking at this graph you can infer this, that at x equals to a, the function has a minimum value, and since it is based on the entire domain of this function, right? It is based on the entire domain of this function, you will call this maxima as the global maxima. Similarly, at x equals to b, this function has a global minima. This function has a global minimum, right? I hope this is understood. Okay, now if you again look at this graph carefully, do you think that this is the only maxima and the only minima that this graph has? If you consider this entire domain, then yes, this is the only maxima and this is the only minima. So in this sense, we can say that global maxima and the global minima are unique. There is only one single global maxima and there is only one single global minima. Now, what about these 2 points, x0 and x1? If you say x equals to x0, then what you see, the function has a dip at this point. Here you see that the slope is decreasing. Here the slope is constant or zero, the slope is zero, sorry, and then it increases again. So corresponding to this point, you see a dip in the function. Now, if you consider a small interval around this point, if you consider a delta neighborhood of this point, so you're considering this portion x0 minus delta to x0 plus delta, where delta is a very small quantity greater than 0, right? So if you consider only this interval and you draw this and you draw this, you consider these range, then what do you think? What is the lowest functional value? What is the lowest functional value? The lowest functional value would be corresponding to this point x0, right? The lowest functional value, let me erase it and say it again. Erase this and say this again, that if you consider a small delta neighborhood around this point x0, and if you check the functional value at all these points, right? At all these points up till this range. Up till this range, if you consider these points, you will see corresponding to the value x0, the functional value is the lowest. So here you will have something fx0, right? Functional value is the lowest. So here x equals to x0 will give you local minima. X equals to x0 will give you a local minima. Why local? Because you are considering it only in the neighborhood of the point x0. Global will be on the entire domain of the function and local would be on a small range, or you can consider it to be a delta neighborhood of the function. If you see in the delta neighborhood of the function, it has a minima, then you will call that minima as the local minima. Similarly, let me erase this and consider the point x1. Similarly, you can consider a neighborhood here, small neighborhood, local neighborhood, and then if you see in this neighborhood, if you consider the functional value at all these points, you will see at x equals to x1, where the functional value is fx1, this fx1 is a local maxima. In this range, in this particular neighborhood, this is the maximum functional value that you can attain. So x equals to x1 will give you local maxima. I hope this concept is clear. This is the most crucial part of understanding in this chapter. We will see how to find out this local maxima and local minima later on. But as of now, this is the thing that you should know, that sometimes we don't have the entire domain with us. In case of, you can consider the production process, or you can consider the utility maximization process. So in these cases, you might not have the entire domain with you, but you want to consider the local. In the local sense, what is the optimum value in certain range? Suppose you are wanting to produce 10 units of, so your capacity is producing 10 units of goods, right? So you will see what is the optimum production in this 0 to 10 units. So you can produce 0 to 10 units of goods. This is your capability. Now you want to determine which is the actual production. If I produce, suppose I produce 7 units of good, and that will maximize my revenue, or that will maximize my profit or not, right? So in this way you are calculating these. Economists do this in this fashion, that they always want to find out the optimum value of the choice variable, so that their process profit, or their total revenue, or their total satisfaction is always maximized, or their cost is always minimized, right? Okay, so this is what I have written here, is that we say fx has a global maximum at x equals to a, global minimum at x equals to b, it has a local minimum at x equals to x naught, and a local maximum at x equals to x1, right? And our primary purpose of this chapter is to see how we can locate the position of the local maxima and the local minima for a smooth function. Where you see that this is a smooth function, it will not work if you have some kink point or something like that, because at the kink point the derivatives will not exist, right? This we have discussed in our differentiability chapter as well. So for applying the method that we will be talking about in a minute, you will have to have a smooth curve, right? A smooth curve where the curve is continuous and twice differentiable actually. So in case of a smooth curve, we'll see how to find out the local minima and local maxima now. Okay, so let me start with that. So the process is, you have to find out the first derivative test. You have to find the first derivative. How to apply this test? Look at this graph. This is a concave function. If you have seen my video on concavity, convexity, you will know that the curve is above the line. If you draw this line, the curve is always above the line, and this is a concave function in that way. Okay. Now if you consider the tangents, the slope, tangent is nothing but the slope. You see that initially it is increasing, it is again increasing, but at a decreasing rate. At this point the slope is 0. At this point the slope is 0. It is a straight line parallel to the x-axis. Then the slope is again decreasing and it is decreasing. So initially it is increasing, but increasing at a decreasing rate. Then it is getting straight parallel to the x-axis. That is, the slope is 0, and then it is falling again. Now what does this tell you? This basically tells you that for the value x equals to x naught, or for the value corresponding to the maximum value of the function, the first derivative or the slope has to be 0. The first derivative or the slope has to be 0, that is the tangent has to be parallel to the x-axis. Similarly, if you consider this is a convex function, line is above the curve. Here you see the slope is falling, then it is falling, then it is again getting straight here, so it is slope is 0 here, and then it is increasing. And corresponding to this, you see that this is the minimum point the function can attain. Here, corresponding to x naught, in the relative sense or in the neighborhood of this point, you see this is the maximum functional value that the function can attain. After this point this is falling, after this point this is falling. This is the maximum point. Here also this is the minimum value in this neighborhood of the point x naught. In this neighborhood, initially the value is lower, it gets minimum here, and then it again increases. So in this neighborhood you will see this is the lowest value or the minimum value that this function can take, and this again happens corresponding to the point where the slope is 0. So this slope equals to 0 gives you the first derivative condition, or what we call as the necessary condition. What we call as the necessary condition of the optimum value, or finding the optimum value or the extremum value. So here I have written is that by drawing tangent lines to the curves in the near neighborhood of the local maximum and the local minimum, it is obvious that at this point tangents are parallel to the x-axis, so that this is satisfied. So dy dx is again f prime x, This is the same thing. At the value x0, if you calculate at the value x0, this will be nothing but 0. So this is the first order necessary condition, which is also known as the first derivative test of for both finding the maximum value or finding the minimum value in the local sense. In the local sense. Okay. Now why this is important? If you equate this, you will get something called the stationary point. So points on the curve y equals to fx at which df dx is 0 are called the stationary points, or what you call as the critical points. Is called the critical points, right? So stationary points or the critical points of the function. So these are the potential points at which the function might take the maximum value, local maximum value, or the minimum or the local minimum value, right? So stationary points give you the potential points at which the function have the extrema, either in the form of maxima or in the form of a minima. Now, one thing you need to be careful about is that a stationary point is not necessarily a local maximum, local minima. So if you equate this thing and you get some value, now by just getting this value, you can't say that okay, this is maxima or minima. So for that, you have to satisfy the second order condition. So stationary point does not necessarily the local maxima or the local minima. It could be the point of inflection as well. So it is the df dx equals to 0. It is the necessary condition. It is the necessary condition, but not sufficient. But not sufficient. Right? So you can't stop by only finding out the first order condition. You can't only find out this. You have to verify that the point that you have found out is either maxima or the minima or not. Now for distinguishing this between these two, you have to find out the second order sufficient condition. Second order sufficient condition, what you also call the second derivative test, where what you have to do, suppose if you have x naught as the stationary point of this function, so you have found out df dx, and you see that at the value x naught, this value is 0, df dx is 0, the tangent is parallel to the x-axis, so you know that that is a stationary point. Now what you do for finding the second order condition, you will say that the function has a local minima at point x naught if the second derivative at x naught is greater than 0. You will say the function has a local maxima at x equals to x naught if the second derivative is less than 0, and it is inconclusive, or it is a potential point for inflection if the second derivative is equals to 0. Now why this is so, if you have seen my video earlier, I told you second derivative ddx of df dx gives you the curvature of the function, or it gives you the nature of the slope of the function, right? Second order derivative gives you the curvature of the function, that is the nature of the slope of the function. Now previously, if you have seen this, I have already told you that for a local maxima, this is the local maxima case. For a local maxima, the curve is concave. You have to have this shape. The curve is above the line segment. If you join any 2 points with a line segment, the curve will be always above the line segment. So this is the definition of concavity. If you have seen my video, then you will understand that for a local maxima, the curve has to be concave. And if you remember, the condition for concavity was that if double prime x is less than 0. So on the left hand side, the derivative is positive, or the ddx is positive, but on the right hand side, the derivative is negative. That will give you the slope will be increasing but at a decreasing rate, which will be given to you by the second order derivative, which is less than 0, right? Now for this case, which is the local minima case, you have initially the slope was falling, and then the slope is increasing. So the curvature is basically increasing. After this point, you see the curvature is increasing. After this point, you see the curvature is decreasing. So here the double derivative is negative, here the double derivative is positive. And this is the exact condition we are checking here. That if the double derivative is positive, it means that after this point, the slope is increasing. here you have the double derivative to be negative. After this point the slope is decreasing, so this will give you local minima, this will give you local maximum. And we will discuss this third case where it is inconclusive in nature, where the second derivative is exactly equals to 0. We'll see what to do with this condition. Okay, now if you want to know more explanation, I have given you that as well, that this is the same thing, that to the left of the minima this is negative, the slope is negative, to the right it is positive. So for a relative minima, this is the thumb rule, that for a relative minima, if prime x has to change its sign from negative to positive, from the immediate left of x naught to the immediate right. So this is what you see here. And for a relative maxima, the derivative changes sign from positive to negative, from immediate left to the point x naught to the immediate right, which you see here. So to the left this is positive, and to the right the slope is negative. I hope this is clear. Now this I have got from a book. I have given you the screenshot of this. And if you want to know this interpretation of the second derivative in a little more detail, you can pause the video and read this. This is very simple. This is nothing new. I have told you already. And this is the summary of what we have studied so far. So the first order condition, necessary condition for both maxima and minima, is that the first derivative has to be 0. Now second order necessary condition is that if prime x is less than equals to 0, for minima it has to be greater equals to 0. And the sufficient condition is that if the strictly inequality holds, it is strictly less than 0 and it is strictly more than 0. And these conditions will only apply after the first order condition is satisfied, right? So you have the critical points with you, only then you can check this sufficient conditions. Okay. Now that we know what is relative minima, what is relative maxima, how to find them, what are the necessary and sufficient conditions for them, now we have to know the third condition that we have, what we have told to be inconclusive condition. What happens if the second derivative is also 0? So first derivative is 0. Now you see that the second derivative is also 0, right? Second derivative is also 0. Now what do you do? How you conclude anything from this condition? The second derivative equals to 0 gives you a potential for the existence of a inflection point. Gives you a condition or a potential for inflection point. What is an inflection point? Inflection point is a point that divides the curve into two different phases, where in one phase the graph is either concave convex, and in the later half it is either convex and concave, right? So let us see this graph. So here basically what happens, the function changes its curvature at this particular point. So if you see this graph at the point x naught, what you see, the function changes from concave to a convex function. Here if you see here, at the point x naught, the function changes its curvature from convex function to concave function, right? So here initially it was concave, and after this point here the function becomes convex. If you don't know how to check this, how to visually analyze this, I will give the link of the concavity convexity video in the description. You can check that out. And here if you see, it is initially convex, and after this point this becomes concave. So inflection point gives you that point, that particular point, which basically marks the change in the curvature of the function. Simply this. If you see this graph, it will be more clear. So inflection point is this point, xi. Xi is the inflection point. This is x, this is xi, where when x equals to xi, this will give you the inflection point where the function changes its curvature. Here you see it is convex here and it is concave here, right? Now how to find this? Now how to check that there exists an inflection point or not? So for that, simplest way is, again, if you plot this, you can visually analyze that to the left of point x naught the slope is positive, to the right of x naught the slope is also positive. So initially what we were seeing in relative minima maxima case, these were two opposite sides, right? So here the difference is that here to the left and to the right both the slope is both positive. So here you see this is positive and this is also positive, and here if you see both are negative, here also it is negative, here also it is negative. So this is one of the process of checking inflection point. Here is the details I have given you. If you want to know more about inflection point and how it is used in economics, you can pause the video and take a look at this. And we will be solving a couple of questions now. So using questions, we will see how we can find out relative minima, maxima, and inflection point. And if you are with me till now, and if you find this video helpful, then don't forget to subscribe to my channel. I'm putting in a lot of effort to explain things to you. So if you find this helpful, then give me a like and do subscribe to my channel. Okay, now let us come to some of the questions. This will make your concepts even more clear. So question number 1 says sketch the curve y is x minus 2 square plus 2 and locate the stationary points on the curve. So what you can do from here is that y is given to you as x minus 2 square plus 2, and you have to find stationary points. So you know, simply you have to find out dy dx and equate it to 0. Do that. Dy dx, which is also f prime x, which will be 2 into x minus 2. Right, now from the first order condition we know f prime x has to be equated to 0 for both local maxima and minima. So 2 into x minus 2 is 630, and it has only one stationary point. You can consider it to be x naught. It is 2. So from the graph, you have to draw the graph. How would you draw the graph? Firstly, know the stationary point. So you know that at this stationary point you have either local minima or local maxima. Now for drawing the graph, you need one more thing, that is the curvature. For that, what you have to do, find out d2 by dx2, which is the second derivative for the curvature. Here if you see, it is 2, which is strictly positive. So what you get, second derivative is strictly positive, which means that the function is convex. This is the condition of checking convexity for a single variable case. This also I have discussed in my video, so go check that out. And in this way, so you know that here you have a critical point or a stationary point, and also you know that the function is convex, right? The function is convex, so that will give you this particular curve. Now this is a homework for you. This is the similar question that we have solved, that locate the position of the stationary points of this. So this is a cubic function, and simply what you have to do, find out dy dx or f prime x and equate it to 0, and that would give you your stationary points. So please do this question and let me know how many critical points you get and what are they, right? What are those? Okay. Let me go to question number 3. It says find the stationary points of the function fx is x cube minus 6x. Now it says what are the stationary points, and are the stationary points local maxima or local minima, right? So here you have to check both the first order condition and the second order condition. The first order condition is f prime x is 0. So do that. Find out the first order condition. This equated to 0. So it will be x square minus 2 equals to 0, or x is plus minus root 2, right? If you take this here, it will be plus minus root 2. Now what is the second order condition? First we find out f double prime x. What will that be? It will be 6x, right? You are taking derivative of this, it is 6x. Now for local maxima or local minima, what you have to do, find this double derivative at this critical point. So you have two critical points here. One is x is root 2, another one is x is minus root 2 here, right? So put root 2 here. So it will be 6 root 2, which is positive. Now if the second derivative is positive, you can say it has a local minima, right? Second derivative is positive, means local minima. And if you find this, it will be 6 root 2 minus 6, which is negative. So you have a local maxima. So here I am just applying this. If you see this, so I have found out if prime x equals to 0. Now for taking the second order condition, I am just finding out the second order derivative, and then we can conclude from here that yeah, This is the local minima and this is the local maxima, right? Now how to find out the value? Just simply put root 2 here and minus root 2 here. You will get the absolute value of the function. So functional value would be 2, and if, sorry, it's not 2, it's root 2. So root 2, f of root 2. This will give you your point as the local minima, and minus root 2 and f of minus root 2. So simply put minus root 2 here and root 2 here. This will give you your local maximum. And this is the way you find stationary points as well as local, and check how to identify their local maxima or local minima or not. So this is the way of doing that. Okay. Now this is the fourth question. This is again your homework. That this is the same question, that find out the local maxima and minima. So again you have to do dy dx, set it equals to 0. That will give you your first order condition, and this will give you your stationary points. And then you have to check the second order condition, find dy by dx2, and check that on this stationary points and find out they are less than 0, equals to 0, or greater than 0. Right? This will give you your criteria of local maxima and local minima. Now this is an important question which says that determine the inflection point of the given function. Now I'll show you how to check for an inflection point. You have this function. For inflection point, find out this 4x cubed minus 48x, right? Here you have x to the power 4, 4x cubed minus 48x. Yes. Now find out the double derivative. What will that be? This. Now for inflection point, I have told you that the second derivative has to be equated to 0. The condition is the second order derivative is equals to 0. So you have to do that. Find out the second order derivative and then set it equals to 0. So this will give you x square minus this, and x square is this. So x is plus minus 2. Root 4 is basically x is plus minus 2. So you have, what you have here is that you have two potential inflection point. One is x is plus 2, another is x is minus 2. Now how do you know that they are actually inflection point or not? So the first approach of checking that is find out the third derivative of the function, right? The first approach would be find out the third derivative of the function. What will this be? This will be 24x. And now at these points where what you get by equating if double prime equals to 0, these are 2 points. So check this third derivative at these 2 points. 24 into 2, this is not equals to 0. Again check this third derivative at minus 2, this is 24 into minus 2, which is also not equals to 0. If you see the third derivative is not equals to 0 at these points, then you are certain that these 2 points represent inflection point, right? Inflection point. So this is the first way of doing things, that equate the second derivative equals to 0, you will get some points. These are your potential points for inflection point. Now how to know that they are actually inflection point or not? First find out the third derivative, and then in that third derivative put this x values, x plus 2 minus 2. If you see that at these points this third derivative is not equals to 0, you will say that x equals to 2 and x equals to minus 2 both are the inflection points. So at both these points the function changes its curvature, right? This is the first approach. Now there is a second approach, how you can check the inflection point. So what you get from this is that x takes 2 values, x is either 2 or x is minus 2. Say I call it x1, I call it x2, right? Now for checking this will be an inflection point or not, what you have to do, consider a point which is smaller than this value and consider a point which is greater than this value. Suppose I consider the point, suppose x prime is a point which is 1, which is less than 2, right? And x double prime is a point which is 3, which is more than 2. Now check the double derivative at these 2 points. The double derivative here, what is the value? It is 24. Oh no, sorry. The double derivative at 12x square minus 48. 12x square minus 48. This is less than 0, right? This is 12 minus 48, which is less than 0. Find out the double derivative at this point 3. 12x square minus 48. If you do this, you will see it is greater than 0. Now, if you see, they are opposite in sign. They are opposite in sign. So, graphically, if you want to know, this is 2, this is 1, this is 3. So, what you said is that at x equals to 2, if double prime is 0, at x equals to 1, you just found out that it is if double prime is less than 0, and at x equals to 3, the functional value is more than 0. So what you can say is that the function changes its curvature at the point x equals to 0, because initially it was negative. Initially it was negative means that the function was initially concave, right? Double derivative is less than 0 means the function was initially concave. At this particular point, this is not changing its curvature since it is the inflection point. And then after this point, the functional value, the curvature is greater than 0. It means that it is convex. So the function is initially concave. It tells you, the opposite sign basically tells you the function was initially concave, and then from the point at the point x equals to 2, it changes its curvature and it becomes a convex function. So it ensures, this condition ensures that x equals to 2 is an inflection point. I hope this process is understood. It's very simple that if you want to know this point is an inflection point or not, simply take a value lower than that value and simply take another value more than that value and check them at the second derivative, not in the first derivative. Second derivative gives you the curvature, so put that in the second derivative and see if these values are opposite in sign. If these values are opposite in sign, you are confirmed that this is a inflection point. Similarly, you can do this for this point as well. So take one value, suppose I take this to be minus 3 and take another value, say this is minus 1, and then you have to simply check the double prime value at minus 3, double prime value at minus 1, minus 3 square minus 48, and this will be square minus 48. So this will be 9 into this will be positive, and if you see, this will be negative. Again, what you see here is that they are opposite in sign, so x equals to minus 2 is also an inflection point. So what you conclude from here is that this function has two inflection points. One is 2, and if you put this functional value here, this is 1 point. If you want to know xy coordinates, so you have to write in this way. So calculate this, put 2 here and write that value here. And another point is x minus 2 and x minus 2, right? So these are the two inflection points that you have. And I give you two approaches of knowing that they are inflection point. One way would be to simply find the third derivative and see at this particular value they are 0 or not. If it is not equals to 0, it is inflection point. And another way is taking the values. I hope this is understood. Okay. Now, since I have told you that optimization is very important from economics point of view, so I have given you an application of economics using the cost function and the production function. So let's see this question. Question number 3, it says a firm has the following total cost and the demand function. So cost function is this cubic function, and this is the inverse demand function that you have. First question says, does the total cost function satisfy the coefficient restriction of 9.5? So it is taken from a book. I have given you this. So this is the condition that you have to verify, that if this is the total cost function a q plus b q square plus c q plus d. So this function, imitates this form, right? If you compare this with this, you will see this function is in this format. And next you have to check these restrictions, if the function satisfies these restrictions or not. So let us check that. So if you compare this function and this function here, you will see a is 1/3, b is what? b is minus 7, c is this, and d is 50, right? B is 50. Now check this criteria. A, C, D is positive. A is 1/3, which is positive, C is 111, which is positive, and D is 50, which is positive. B is less than 0. Yes, B is minus 7, which is less than 0. Now check this, B square minus 3AC. B square is minus 7 square, 3 into A into C. So this is 49 minus this will cancel out this. This is definitely less than 0. So it will give you this criteria. So this criteria is also satisfied, right? So B square minus C 3AC is less than 0 means that B square is less than 3AC. So this question is done. Now come to the second question. Write down the total revenue function R in terms of Q. So what will be the total revenue function? Total revenue in terms of Q, right? Total revenue is price into quantity. This is the total revenue. The price or unit price into the quantity. Now P, you will get P from the demand function, the inverse demand function. If you take this side and let it come this side, it will be 100 minus Q. So you get that now. So P is 100 minus Q from here, right? This is the total revenue into Q. So this is 100 minus, let me write this better way. This is 100, right? 100 minus Q, this you get from the inverse demand curve into Q. So your total revenue will be this. This is your total revenue. This is question number B. Pretty simple. Now let us do the third part, formulate the total profit in terms of Q. Now what is profit? Profit will be total revenue minus total cost. So total revenue is this which you have found out earlier, and then minus the total cost. It is 1/3 Q cube minus 7Q squared. Then you have plus 111 Q plus 50, right? 111 Q plus 50. Yeah. So this you can simplify further. I'm not doing that, but you can take the subtraction and that will give you your YQ, right? This is the profit in terms of the total quantity. So it's simply revenue minus the cost, nothing else. Now find out part D, which says the profit maximizing level of Q star. So you need to maximize this profit function subject to Q. Now for doing that, what you have to do, the first order condition is simply what we have discussed so far, this. So take that first derivative here, it will be 100 minus 2Q minus 3 will go out, so you have only Q squared. So this part is 1/3 into 3Q squared. So 3 will cancel out and you will have only Q squared. Plus minus minus plus, you have 14Q minus you have 111. Yeah, and you have to equate it to 0. If you take that to this side, this will be Q squared. This was initially yes, so do that. So in this side, this is positive 12Q negative. This would be negative. Here you have minus 11, so it is 11. Okay. Now Q square minus 11Q minus Q plus 11 is 0, so it will be Q minus 11 minus Q minus 11 is 0. So simply Q minus 1 into Q minus 11, which is 0. So what you get from here is that Q has two stationary points. Q has two stationary points, one is this and one is this, right? If you equate it to 0, so you will have either Q is 1 or Q is 11. Now you have to check at this which value it is optimal. Let's go to the question. Find out the profit maximizing level of Q star. So you have to find out at which level of output the profit is maximum. Let's do that. For that, you have to find the second order condition, find out phi double prime Q. What will that be? So this was your first derivative. Now take the second derivative, minus 2Q and anything else plus 14, right? Plus 14. So this will be 12 minus 2Q. Now check this at the value Q at 1. So it will be 12 minus 2 into 1, which is 10, which is positive. and if you check it at the point 11, 12 minus 2 into 11, so it will be 12 minus 22, which is minus 10, which is negative. So what you know, if the second derivative is positive, it is local minima, which is of no use because you want to maximize your profit. So local minima is not something you want. So and this is local maxima. This is the local maxima you want. So at q equals to 11. So what you get from here is that at q equals to 11, your profit function is maximized because it satisfies both the first order condition and the second order condition. And the final part says that, so this is the profit maximizing output you have, profit maximizing output, right? And the final part of the question says that what is the maximum profit? So simply you have the profit function here. This is the function, right? In this function, so at the profit function, if you put q star equals to 11, you will get the maximum profit. So I'm just giving you the expression 100 q minus q square. 100, okay, 100 q minus q square, then what you have, minus 1/3 q cube minus 1/3 this cube minus 7q square, 7q square, then you have plus 100, 111q plus 50, so 111q plus 50. And if you calculate this expression, you will get the maximum profit. So pi max will be at the value q star 11, and this will be the expression. So we have done all 5 parts, and in this way you can solve the economic application questions as well. And this could be your utility function questions as well. Production problems are very common here. Utility maximization or the cost minimization problems are also common. I will see if I can get some more questions on this. I'll see that in some other videos. And the final thing here that we want to know is the nth derivative test, which is the generalization. What we have learned so far is only involving the first derivative and the second derivative, and in inflection point max you have gone into the third derivative case. But this formula or the process that we have discussed is not limited to only these three derivatives. It can be generalized into nth derivative test, and for that you have to follow this rule. Suppose the first derivative is 0 and you get the stationary point as x naught, right? F prime x naught is 0. If the first non-zero derivative value at x naught encountered in the successive derivation is not equals to 0, then it is a stationary value, and this is the formula for that. I will be showing you how we get this. A relative maxima will be when n is even number. This is the important thing. When n is, you can conclude anything if you find the derivative at the even number term, right? If n is even here, if n x naught is less than 0, then you have relative maxima, and if n x naught is greater than 0, it is a relative minima when n is an even number. And again, you can't conclude anything, or you can have an inflection point when n is an odd number. Let me show you formally. Okay, let me erase this. Okay. Let me show you how we can conclude something from here. So it basically says this. Suppose you have a function. What is nth derivative test? You have a function. Firstly, what you do, you have to find out f prime x in every case, and you have to set it equals to 0. That will give you a stationary point x naught. This is what you know. Now suppose you find the second derivative at this value x naught and you see it is 0. Now see, we have discussed that if second order derivative is 0, there is a potential for inflection point. You can find the third order derivative at x naught. If you find that this third order derivative is not equals to 0, you will say it is an inflection point. But what if this third order derivative at x naught is also 0? Then what you can do, you cannot conclude anything from this also. Then you have to find the fourth order derivative. Right? If the third order derivative at this critical point is again 0, you have to find the fourth order derivative at x naught. Now if you see that it is greater than 0, then you will say it is the local minima. If it is less than 0, you will say it is the local maxima. If it is even term, right? Fourth is even, 2 is even. So in even order terms, if you see that it is greater than or less than 0, you can say that it is local minima or local maximum. But what if this fourth order derivative is also 0? Then again you can't say anything from here. You have to calculate the fifth order derivative and set it and see at the critical point. Now at this critical point, okay, right, at this critical point, if you see that it is not equals to 0, you will say that there is an inflection point. But what if this is again equals to 0? Then you have to calculate the sixth order derivative at x naught. Okay, if this is greater than 0, again local minima, and if it is not, then you will say local maxima, and in this way this process will continue, right? So what I'm trying to say here is that it is not limited to the first derivative, second derivative and third derivative. It can continue, it can go on like this, on and on like this. You have to follow this process. I hope this is clear. If you have any doubt, you can let me know. And this is the generalization that I am talking here, right? This is the nth derivative test. You can take a screenshot and then match it with my explanation. This is the formula which I have told you here. Okay, and this is the final question on this nth derivative generalization which I want to discuss with you, and after this I will wrap this session. So it says that y is this. This is the function that you are talking about. You want to know what is the relative minimum, maxima, and so on. So you find the first derivative. Here the solution is also given that if you take f prime, it will be minus 4, 7 minus x cubed. Now what is the stationary point then? X equals to 7 is the stationary point. If you take x equals to 7, the f prime will be 0. Right. Now what you do, you find the second derivative, if double prime x, which will be 12, 7 minus x square. If you again put 7 here, because 7 is the critical point that you have got, if you put 7 here, you will see f double prime is also 0. So you can't conclude anything from that. Check the third derivative, find out the third derivative and compute it at x equals to 7. You see again it is 0. So if the third derivative is 0, you can't say that the second derivative here, there exists an inflection point. So you can't say that, because the criteria is that the third derivative, if it is not equals to 0, then you can say that the point that you got in the second derivative has an inflection point. So this is not the case here. It is not 0. So it's not applicable. So if the third derivative is also 0, you calculate the fourth derivative. Here the fourth derivative is coming out to be positive. Now since it is the even ordered derivative, so 4, here you have 4. Only the even ordered derivative gives you any conclusive answer, right? So remember this thing as a thumb rule, only the even ordered derivatives will give you any conclusive answer. So if 4x, fourth order derivative is positive, the fourth order derivative is positive, we'll say there exists a relative minima. Right? The criteria is the same, only the order is increased. So fourth order derivative is greater than 0, it is relative minima, and we conclude that the point 7, 0. So the point is 7, critical point is 7, and the functional value at that point is 0. So 7, 0 represents a relative minima. And if it would have happened that if 4x is less than 0, we would call that as a local maxima. And if suppose that this was again coming out to be 0, then we would have gone to the fifth order derivative, and if that fifth order derivative would have been not equals to 0, we will call it an inflection point, and if it would have been 0, then we will again compute the sixth order derivative, and so on and so forth. And this is the process of generalizing things and doing nth derivative test. Now with this we finish up everything that you need to know about single variable optimization. I have covered entirely. And if you have any doubts from any parts of this chapter, you can let me know. Please do the homework questions and let me know what you get as the answer. And if you like my video, do give me a thumbs up and don't forget to subscribe to this channel, AN Economist. Thank you for your time.